These are the Unit 1 notes for Earth Science. The first unit is called Earth's Place in Our Universe. So we're going to start by talking about the sun. The goal of the sun is to describe the characteristics and the anatomy of the sun. All right, so the sun is very large and very hot. It is about 100 times the diameter of the Earth, and it's about 500 degrees Celsius, and that's just at the surface. So there are other parts of the sun that are even hotter than 500 degrees Celsius. The sun originally formed from a swirling cloud of gas and dust about 4.6 billion years ago. That cloud of gas and dust is called a nebula. 4.6 billion years ago, the sun was the first part of the solar system that was formed after the Big Bang. The sun is mostly made of two elements. Most of it is hydrogen, about 91.2% hydrogen, and then 8.7% helium. So the anatomy of the sun, there are 6 different layers. In the very center, we have what we call the core. In the core, that is where hydrogen fuses together in order to form helium, and that is the hottest part of the sun. We'll learn more about nuclear fusion in a little bit, but nuclear fusion, that process releases a huge amount of energy. So when that is taking place in the core of the sun, it's obviously going to release a lot of energy, and that makes it very, very hot. So the hottest part of the sun is the core in the center, hydrogen fusing to create helium. Next layer out is the radiative zone, and energy from the core is slowly going to radiate through that layer. As you can see by these little arrows, the energy is moving from the core to through the radiative zone to the outer layers. It takes over 100,000 years for one photon, that means like 1 unit of light, to escape from the core through the radiative zone. So 100,000 years, very, very long time for it to move. Next layer out is the convection zone. So the convection zone, just like it sounds, has convection taking place. That's where the hot plasma is going to rise, cooler plasma is going to sink, and that's how it's going to transfer that heat energy to the surface of the sun. So you can see in this diagram, the convection zone has these like circular motions. That's the process of convection. So heat rising, cooler plasma sinking. That cooler plasma is going to get some of the energy from the radiative zone and then rise again, and that's just going to continue. So radiative zone, heat is moving out. Convection zone, the heat is cycling that plasma. Next out, we have the photosphere. The photosphere is just the surface of the sun, that very outside layer. So the photosphere is that kind of outside layer. It's after the convection zone. From there, we have kind of like the atmosphere of the sun, so to speak. So we have the chromosphere and the corona, which is the atmosphere on the outside. You can see from this diagram as well that the chromosphere and the corona are hotter than the surface, which would be the photosphere. So the photosphere is about 6,000 degrees Celsius. The corona is about 1,000,000 degrees Celsius. You can see that's the part that kind of is furthest away. And then the chromosphere can get up to 10,000 degrees Celsius. All right, so the process that actually powers the sun and creates the energy for the sun, it's a process called nuclear fusion. So there are 2 different processes that have similar names: nuclear fission and nuclear fusion. We're just going to be talking about nuclear fusion right now. So the pressure from fusion pushes outwards, and then gravity is pushing inward. So those 2 processes are what make the sun that actual round sphere shape. So outward pressure from fusion, gravity pushing down inward kind of keeps the sun all together. So changes in the sun's magnetic field is going to cause those phenomena, things like sunspots, solar flares, and coronal mass ejections. We're not going to talk a lot about those in class, but if you hear those come up in the news, sometimes you'll hear about a particular solar flare happening. Just know that those are caused by changes in just the magnetic field that the sun naturally has. So let's talk more about nuclear fusion. The goal for this section is to describe the process of nuclear fusion and how it creates elements. So the process of nuclear fusion combines small elements like hydrogen, into larger elements. And as it combines those elements, it's going to release a large amount of energy. So below you can see a diagram of this process. So we have the section labeled A, which is hydrogen. So you can see there's two different hydrogens. For right now, don't worry about why they look different. The most important part is that they have one proton each. The proton is in blue in this diagram. So they both have one proton, meaning they're both hydrogen. So hydrogen is going to be at the beginning of fusion. Those two atoms are going to fuse, that process of nuclear fusion happening at C, in order to create a new different element, helium in this case, which is B. As it creates helium, it's going to release a large amount of energy shown by D, and this energy is in a form called gamma rays. All right, so we have two hydrogens fusing together to create helium, a larger element, and releases a large amount of energy. This is where the energy for the sun and all of the other stars comes from. It's from this process of fusion. Fusion only occurs in stars, at least primarily in stars, because it only occurs at extremely high temperatures and pressures. So the temperatures needed and the pressure needed is very, very high, so it's very difficult to replicate on Earth, which is why this is a process very unique to stars. Going along with nuclear fusion is this idea of nucleosynthesis. Nucleosynthesis is the formation of heavy elements, which are the nuclei of atoms that have a lot of protons and a lot of neutrons. Remember, hydrogen only has one proton, helium has two protons. When we talk about heavy elements, we're talking about, 10, 20, 30 protons. So the way that nucleosynthesis happens is that these lighter elements are going to collide, undergo fusion, and the result is a heavier atom. So you can see in this diagram, we have helium. So that helium was created in nuclear fusion like we talked about before. Now we have two helium atoms that are going to collide through nuclear fusion again, release energy in the form of gamma rays, which you can see here. And it's going to form a heavier element, in this case, beryllium. So you can see helium has two protons. Well, 2 plus 2 is 4 protons. So beryllium has 4 protons. Then that can combine with helium to create something with 6 protons, releasing a bunch of energy. And again with helium to have 8 protons and release a bunch of energy. So this can continue for many, many different stages in order to create heavier elements. All of those elements are created through that process of nuclear fusion. Every element heavier than hydrogen can be created with nuclear fusion. So the hydrogen in the universe came from the Big Bang. All of the elements heavier than hydrogen were created through this process of nuclear fusion. Massive stars, so these are stars that are much, much larger than our sun, are going to create the heavier elements. So the bigger the stars are, the heavier the elements they make. Our sun is a relatively small star, which is why it's mostly hydrogen and helium. It doesn't have a lot of those heavy elements. You can see in this diagram, our sun is this little tiny yellow dot, right? Here's other stars that are smaller than the sun, but then we have these that are much larger. So look at like Pollux or Rigel or Aldebaran, or this giant red one is actually Betelgeuse. So if you think about Betelgeuse, this star, it's huge. It's massive compared to the sun. That's where those really heavy elements like iron are going to be created right in the core of that star through that process of nuclear fusion and that idea of nucleosynthesis, of those small elements combining to form heavier and heavier elements. All right, so we have talked a little bit about what powers stars. But let's talk about the actual life cycle of a star. So the life and the death of different stars. So the goal of this section is to describe the main events in the life cycle of a star. So first we have to know what a star is. Stars are spheres of matter that have mass and they have energy great enough to cause nuclear fusion, like we just talked about, resulting in the emission of light. So all of that energy that's created through nuclear fusion is what makes stars glow. That's why they have light. That's why they give off heat, like our sun provides heat for us. It all comes from that process of nuclear fusion. So all stars are going to begin their life in a nebula, which is a dense region of gas and dust inside of a galaxy. So we talked about this before. That's how our sun started. All stars are going to start as a nebula. This is a picture of a nebula taken from the Hubble telescope. Galaxies may have many nebulas. Over time, that dense region of gas and dust can form a star. The region of condensing matter is going to begin to heat up and start to glow, and that next stage is called a protostar. Protostar is where nuclear fusion is going to begin. That's when hydrogen, that very light element, is going to fuse together to form helium. That's during the protostar. So first we have nebula, then we have protostar. Every single star is going to have those two phases. The star contracts, so it's going to come together and it's going to begin to glow brightly, releasing energy. That energy comes from nuclear fusion. And now it's called a main sequence star. It's actually a star now, right? The average size star will be able to shine for billions and billions of years until all of that hydrogen is used up through that process of nuclear fusion. Okay, so we have nebula, protostar, main sequence star. Those three things will always be in the life cycle. Main sequence stars have active nuclear fusion happening in their core to create that energy, right? Actively happening to create energy, create light, create heat. Fusion is going to involve hydrogen atoms combining to form helium atoms. About 90% of the stars in the universe are main sequence stars, including our sun. So our sun is currently a main sequence star. Main sequence stars, if we look at what we call a Hertzsprung-Russell diagram, that is like this chart over here, the main sequence stars are going to form this diagonal band kind of diagonally through the center of the diagram. This HR diagram, we're going to look at them more closely in class. It's basically graphing stars based on their luminosity. So you can see luminosity on the Y. The luminosity is always in comparison to the sun. So the sun is considered luminosity of 1. And then it's either dimmer, smaller than the sun, or brighter, larger than the sun. And then it also has the temperature, which is in Kelvin. Notice that the temperature actually goes backwards on an HR diagram. So the hottest ones will be furthest to the left, and the coolest will be furthest to the right. Okay. The next stage of the star's life cycle is going to depend on its mass. So we have these main sequence stars. If it is a small star, meaning about the size of the sun, 1 to 1.5 times the size of the sun, it's considered a small star, and it has a different life, a different pathway. If it's a massive star, that's going to be about 3 times the mass of the sun. That's going to have a different set of stages in its life. So it all depends on its mass, how large it is. So let's start with small stars first. After the main sequence stars, then if it's a small star, the helium in the core is going to contract, meaning it's going to come together. Nuclear fusion is still going to continue to happen, except that all the hydrogen is gone, so we just have helium. That helium is going to fuse together to form carbon. As it's forming that carbon, the outer layers are going to expand and they're going to cool. So the star is actually going to get larger. And that's going to form something called a red giant. When the helium core runs out, meaning the helium is gone, and all of the other outer layers, because remember the star is expanding, when those outer layers kind of drift away, they're no longer being held by gravity to the core. It's that shell of gas that's left is called a planetary nebula. So a planetary nebula is different than the nebula at the beginning of its life cycle. So remember, those are a little bit different. Planetary nebulas only happen with small stars. That very dense core, that core where nuclear fusion was happening, is still going to remain. That's going to become a white dwarf. When that star cools completely, stops shining, we don't have light coming off of it, that is now a dead star, which we sometimes call a black dwarf. Okay, so again, for small stars, we have main sequence. Then we have red giant, where it's making carbon in the center. It's expanding, expanding, expanding. As it expands, it creates that planetary nebula as those layers kind of break away. What's left is that dense core called a white dwarf. When the white dwarf no longer shines and produces energy, it's a black dwarf. Only small stars like our sun will go through that pathway. If it is a massive star, that hydrogen fusing to form helium takes only millions of years. Because it's so massive, it has a fusion happening at a much faster rate. There's a lot more fusion happening, so it happens much faster. So after that main sequence stage, the massive star is going to become a red supergiant. So similar to the small star, right? The same sort of idea, but it's massive. So we call it a supergiant. That helium that's left in the core is going is going to continue to fuse to make heavier and heavier elements, and then that star is going to expand and start to cool, similar to what the red giant was doing for small stars. The helium core is going to fuse into carbon. Once it makes carbon, then it's going to make oxygen and nitrogen and iron. Those later elements are only going to be created in the most massive stars. So remember, the bigger the star, the heavier the elements it created. That's why small stars only go up to carbon, because carbon's not a very heavy element. Once it has that iron core, it's going to collapse in less than 1 second and create this explosion that we call a supernova. This supernova creates a shock wave. It's going to take those outer layers of that star and kind of blow them off. And that supernova is going to shine brighter than the entire galaxy, but only for a very short period of time. So many heavier and radioactive elements are formed by the unstable conditions of a supernova. So once that explosion happens, that a lot of new elements and radioactive things are created through that sort of explosion and release of energy. When a star uses up its last fuel, it doesn't have anything else that it can do fusion with. There's no pressure pushing outward against gravity. Then the star is going to collapse. When it collapses, it can do one of two things. If it is a smaller massive star, it's going to collapse and create a neutron star, which is a very, very dense star. Or if it is a very massive star, so only the largest stars in our universe, is going to collapse and become a black hole. So a neutron star is, remember, that's the smaller of the massive stars, right? When that neutron star condenses and collapses, it's going to be about 1.5 to 3 times the mass of our sun. So still larger than our sun, but much smaller than it originally was. About 10 kilometers in diameter, and it consists mainly of neutrons. So it's very, very dense. So it's all the mass of our sun, but in that 10-kilometer diameter. So very, very dense, tightly packed neutrons. A black hole is only going to happen with the most massive stars. So stars that are more than 3 times the mass of the sun. There's a lot of gravity pulling everything in. There's so much gravity. The gravity is so strong that the light cannot escape. So that's why we call it a black hole. We can only see, and I have that in parentheses because you can't really see a black hole because nothing is there, right? It's pulling everything in. The only way we can identify black holes is by seeing what is being pulled into it. So we can see the gases of other nearby stars that are being pulled into that black hole. So if you look at the picture in the back, you see kind of the gases and the other stars being pulled into that actual black hole. That's how we know that a black hole is there. We can see the strong gravity's effect on everything around it. So again, massive stars are going after the main sequence. We're going to have red supergiants, then a supernova. After the supernova, the smaller massive stars will create a neutron star. The larger massive stars will create a black hole. So here is kind of an outline of the pathway of stars. So remember, all of them are going to start as a nebula. All of them have this protostar phase. This blue one is the main sequence, right? They all have that in common. From there is where it becomes different. So the lower mass star is on the top, higher mass star on the bottom. All right, let's talk about the Big Bang Theory. So I mentioned it before about the Big Bang Theory created all the hydrogen in the universe, but let's talk about how do we know the Big Bang Theory actually happened. So the Big Bang Theory, it states that the universe began as a single point and that it has expanded ever since then. So the universe began as a tiny little itty bitty point and is expanding ever since the Big Bang happened. This is the broadly accepted theory for the origin of our universe. So the universe is everything, not just our solar system. It is everything that exists, right? And it occurred 12 to 14 billion years ago. So the Big Bang Theory happens 12 to 14 billion years ago. Our sun wasn't formed until about 4.5 billion years ago, right? So there was a big section of time where our solar system did not exist and our sun didn't exist. All right, there are 3 main pieces of evidence that we're going to look at for the Big Bang. The first is the abundance of light elements. Light elements as in not heavy, right? Hydrogen is the lightest element, and it's the most abundant element in the universe. that hydrogen was created during the Big Bang when protons and neutrons collided together after those first few minutes of the Big Bang, right? So protons, neutrons are expanding and they have all this energy and they're going to come together and make hydrogen. Then those hydrogen atoms can fuse together to create the next lightest elements, helium and lithium. Those were fused in very early stars, and those are also very abundant in the universe. So most of the elements in the universe are these very light elements that don't have a lot of protons and neutrons. Hydrogen, helium, lithium. That's how we know that those are the first things that came, because most of the universe is made of those things. So like we mentioned before, all elements that are heavier than hydrogen are created in stars in their core during nuclear fusion. Second piece of evidence is something called red shifting. So this is something we can still observe today. Most stars and galaxies are moving away from us because the universe is still expanding. As those stars and galaxies move away from us, we see something called the red shift. The light that is given off is going to be shifted towards the red end of the visible light spectrum. So down here is visible light. You can see that violet colors have the waves very, very close to each other, right? As things move away, those wavelengths stretch and it's going to move closer to the red end of the spectrum. So maybe things were originally indigo. As it moves away, it's going to shift more to blue, then to green, and eventually to red. So that shifting of stars and galaxies, when we view them, they're closer to the red and yellow and orange end of the spectrum versus the blue and violet end of the spectrum because they're moving away. We can tell how far away a star is by how much its spectra is red shifted, right? So if it is very far away, then we know it's going to be much further to the red end of the spectrum. And if it is much closer, it's going to be much closer to the violet end of the spectrum, right? Just remember that red shifting is not the same as a red star. We talked about red star as like a phase of life in a star. Red shifting is not the same as that. These are two distinct things. All right, so a red shifting star basically says that an object can appear any color, but absorption lines are shifted towards the red end because it's moving away from us. So it doesn't mean everything looks red. It just means that their color is shifting towards that end of the spectrum. Okay. Versus a red star is a cool star that gives off more red light than any other color. And then the third piece of evidence is something called cosmic background, cosmic background radiation, not information. So this is believed to have been formed shortly after the Big Bang, and it is this low levels of radiation that are evenly distributed throughout the universe. So when the Big Bang happened, we had that point in time that exploded and expanded to create the whole universe. When that happened, low levels of radiation expanded and distributed and moved throughout the whole universe. And we can measure that radiation. When we measure that radiation, we see that in fact, the entire universe is full of this evenly distributed energy from the Big Bang. So the temperature differences in cosmic background radiation exist today because there's that uneven distribution of matter in the early universe. So matter was not evenly spread out at the very beginning. You can't have temperature without matter. So because matter was not evenly distributed, temperature was not evenly distributed. And this is likely to have caused the formation of the very first galaxies that we had. All right, so those are the end of your notes for the first unit. Please make sure that you submit it all on Canvas, and we will review the information in class.